Thank you. So, thanks for coming. And in the previous two talks, we were discussing the properties of fully non-perturbative S matrices in quantum field theories. So the theory was massive and gap, and we made a lot of use of elastic unitarity. In the last talk, I want to switch to gravitational theories, and the talk in principle could be fully stated in ADS or in flat space because all the ideas are very similar. I will state things in flat space because it's somewhat simpler, and then in the end I will restate them or map them to ADS and CFT. So the talk is based on coming work with Murat Kologlu, Peter Kravchuk, and David Siemens-Duffin. So it's the shocks and superconvergence refer to two aspects of this work. So shocks would be gravitational shocks, and superconvergence is a term again. It's again from 1966, or at least somewhere around that, from the paper De Alfaro, Fubini, Rulan, and Rossetti. But I will explain what it means. So what's the idea? We know that, say, one special feature of general relativity is that things follow geodesics. So if we throw a brick and a feather in vacuum, at least they're supposed to fall same speed, whatever. But if we introduce a modification of the theory, if we introduce some correction to general relativity, in general, things do not follow geodesics anymore. For example, if you just take pure GR and add some high derivative terms, then in principle, if you propagate in a gravitational field a graviton with the different polarizations, they will not follow geodesics. They will have different trajectories. So you can see this violation of usual equivalence principle. And you can ask, okay, if you can add these corrections, things do not follow geodesics anymore, but is it a consistent theory? This work is an attempt to put some bounds or to derive some consistency condition on any gravitational theory, which is a modification of Einstein theory. So instead of throwing bricks, and it's useful to consider a very universal background, which is a shockwave background. So what is a shockwave background? If you have a null source, any energetic particle, its gravitational field is described by this famous metric, where I introduce the null coordinates, U and V, and we have some source that transfers profile in the transverse plane, and it's localized along U direction. We have so the interesting thing, what is the picture is that what is the physics of this metric? It's very simple. So you have a coordinates U and V. There is a shock wave localized at the instant of time here. And it's generated by a stress tensor. This is the nice thing about this metric, and why is it also beautiful, is it's an exact solution, not only of Einstein theory, but if you add any perturbative corrections, any high derivative corrections to it, it's still an exact solution. That's a beautiful fact about that. And in the transverse plane, if you put this y, this is a metric, you compute Einstein equations, you compute the Ricci tensor, you'll find that it has a delta function support as the origin. It's this component HUU, it satisfies just a box in a transverse plane of it is 0, and it has a delta function the origin. So this is your source. there is some particle with a large momentum propagating in this direction, localized in the transverse plane, and it generates this metric. So again, it's an exact solution of Einstein theory. So what happens to you if you propagate through this metric? There are two things. So let's now throw in a particle to go through the shock. Two things happen. First is an effect known as, in the original paper, is a force test of general relativity, which is known as a Shapiro time delay. So you come out later. It's the same fact as radio signals get delayed when you send them back and forth with the gravitational field, and Shapiro time delay takes this form, where this B is nothing but impact parameter. So I mentioned a particle which is in transverse plane is located at some distance B from the center of the shock.
Sorry, so this V is a time coordinate.
B?
No, V.
V, yes. So these are like coordinates. Yeah. So you can.
Sorry.
This, yeah.
So 1 plus 1 MP.
Right. So it's a 1 plus 1 Minkowski, and you get delay.
And the other one is transverse to this.
Exactly. Yes, it's transverse to that. So this is a one effect, and note that it is positive, and there is G Newton here. And that's related to the fact that gravity is attractive, and when you try to make gravity repulsive, you will violate causality. Okay. And the second effect is not very important, but
Sorry, delta? Is delta minus 4, is that the dimension?
let me write a little d, so d is not confusing. So in 4 dimensions, the potential is logarithmic. It's 2-dimensional Laplacian, so it's minus 4. And the second thing which happens, which is also you would expect, because this is an attractive center. So if you started at rest, after you cross the shock, you get a kick towards the center. So velocity in this transverse space gets a kick, and it's related. So this is just a study of geodesics on the shockwave spectrums. Do that, that's it. So let's imagine now the following thought experiment. We take a series of shocks. Another property of this geometry is that you can superimpose these shock waves. Here I added one shock wave here, and at this instant of time you can put many of those. And you can ask what happens as you propagate. Well, what happens, you get these kicks and you get Shapiro delays. Now let me take, so the effect is, I will not focus on the kick, I'll go focus on the delay. And the important thing is that the effect is additive, but also, let's say you choose your shock wave, you arrange them as shock 1, shock 2, shock 3, 1, 2, 3, etc. But also it's, as you see from here, it's a commutative thing. If you propagate your shock waves like this, or you propagate like this, it doesn't matter, because what happens is just delta V's add up the kicks. And let me now, for simplicity.
Sorry, but you are, I see, so you say that any linear superposition is also an exact solution,
yeah.
So they don't
Don't talk to each other.
back react.
Yeah. So, since it's a property of geodesics, and you know that in GR, photons and gravitons and everything follow geodesics, the same is true for geodesic, for gravitons and photons, for all particles. Now,
So I'm sorry, did you say that with every kick you get closer to the, like your impact factor becomes less and less? At least for t larger than 4?
so d larger than 4, you get this d, just the potential decay faster.
Which means that the next phase shift is going to be bigger, or because d is going to be smaller.
Well, it depends how you arrange them, right?
It depends on the center, on the
Depends on
perpendicular.
the centers, we can arrange them as we like. The focus of my talk will be on this part, because as I told you, so this commutativity is a property of geodesics. And then as you will see that if you modify gravity, this will not be true anymore. That would be related to the fact that in gravity, the propagation through in non-minimal theories, propagation depends on your polarization. You do not follow geodesic. It's a very general statement, but one particular and convenient for us version of the statement will be that if you take this background, which is again an exact solution in modified theories, that things do not commute. And then we will try to understand if it's okay that things do not commute. And the claim would be that actually in a consistent gravitational theories, shock waves would commute, and that would be a sort of quantum upgrade of this equivalence principle intuition. And the restoration of commutativity will be mandatory, and it will require, if you want to modify gravity, require general extra degrees of freedom. So that would be the idea. Now this is a geodesics, and if you want to study the problem of commutativity in a quantum theory or in a more general theory, it's useful to go away from geodesics and restate this problem in terms of scattering amplitudes, because it's very general.
Sorry, but you will still be able to see quantum gravity as an effective field theory, or?
Yeah, well, maybe it's I shouldn't go too much into this. It would be just if you have perturbation theory, you still have perturbation theory, but at every order you will have to obey that. So the questions. So I will discuss a few mechanisms how you can modify coupling to graviton on one hand, but on the other hand to have a consistent theory. Now, let me restate this exercise in terms of scattering amplitudes, because no matter what the theory is, we believe there is an S matrix, and so this commutativity is some property of S matrix, gravitational S matrix. So let me consider as you know, and as we discussed in the S matrix, we consider external states which are plane waves. So I'll consider let me say ingoing state will be a plane wave which has some momentum du, then some transverse momentum. And then we want to study, this is plane wave, you can form a wave packet, it will become geodesic. And we would like to study propagation of this wave through the shockwave background. One way to formulate this shockwave background in a way suitable for scattering amplitudes is to consider shockwave state. So what is a shockwave state? States. So shockwave states is the following graviton. So we consider a profile which, for the metric, say, which is purely along this UU component here. But instead of this background, which is a classical solution, we consider, we still want to localize it in the U direction. And we would like to consider some polarization of the shock epsilon1 and the momentum in the transverse plane of Q1. this is a funny state, because if you have a graviton which is on shell, its momentum should be null. Right? We can write this delta U as an integral over a GdV of e to the I pi over 2 dV times U. And so if you compute the total momentum, say, of this plane wave, it's q squared in the transverse plane. So for it to be null, we choose this q squared to be null, which is what we can do. It's not a usual thing. Usually it's a real. So if you wish, it's a funny, slightly funny state. So we consider q1 squared equal to q2 squared equal to 0. So this type of plane waves, we can consider them as the Shockwave states. And yeah, we can consider scattering amplitudes with them. And now we can, of course, introduce here also some u minus u naught. So and we can arrange shift to the center by introducing some shift in the energy.
Sorry, but could you have some problems with unitarity or something like that by choosing complex? I guess no.
Well, we will. In the end, it will be all restated in terms of usual S and T in the complex plane, and unitarity will not be very much role. We'll never use. Yeah, I'm not sure what to say about unitarity, but it's not a physical state. But if we have scattering amplitudes, then we can consider evaluate them at this.
So this one is a perturbation on top of some background, or this is a
this is a perturbation on top of Minkowski. So now I will consider.
No, what I'm trying to understand is that the same shockwave that you're
It's
trying to put there for the background?
Yeah, well, it's the same in the sense that it's UU component and the metric is harmonic, right? This is a harmonic metric in a transverse plane.
Sorry,
yes.
And it's localized in time. And so if I superimpose with some profile in Q, then I will get the previous metric. But now this.
Yeah, but this blows up in some at Q infinity somewhere.
Yeah, sure.
Sorry, not at Q infinity, at Y infinity in some direction because Q is complex.
Yes.
Okay, so it's not normalizable.
Right. So I will be. Well, this is a plane wave with this momentum, which is complex.
It's an exact solution of Einstein's equation, but it has some profile which makes it a large perturbation in some
I think so, right. I agree.
Okay.
Right. So what is this? It's just what we want to consider. If we want to consider the two shock waves, and we want to consider propagation through two shock waves. And the way to do that is to consider a scattering amplitude, to model it. Maybe I shouldn't focus too much on this picture because in the end I don't think it's important. So we consider the following scattering amplitude. So we have a two graviton state, 1, 2, and we have a probe. I want to study a final state, which is also one particle state, as it propagates through the shocks. So that's a setup. And well, I choose momenta to be, say, P1 will be 0 minus PV Q1, P2 will be 0 Q2, and the probe will be have a large momentum in PU. This is a conserving kinematics, and all the Q squares are null. So I choose a slightly, maybe, I'll choose S to be as usual minus P1 plus P2 squared. In this case, it will be minus Q1 plus Q2 squared. And T will be minus P2 plus square. Now, in principle, if the particles, so these guys, they have a polarization along U component, but I have to choose a polarization for the probe. And so I will choose it like this. So for the probe, I will choose a U component of vector D0. V component is fixed by transversality, and the important thing will be the polarization and transverse plane. Well, that's a picture. We take a transverse probe and propagate through this couple of shock waves. Now we can think of this process as, well, what is the transition amplitude between the initial state and final state? With these two guys present, it's a scattering amplitude. And now we can just take a scattering amplitude, evaluate it at these kinematics, and then we arrange shocks at some moments U1 and U2.
So sorry, so this is the S matrix for two shock waves in the background of two other shock waves.
This is a 2-to-2 scattering amplitude.
Yeah.
This is 2-to-2 scattering amplitude, which
Shock waves.
of particles, any particles, say gravitons or scalars. In principle, at this moment you can take, if they exchange a graviton and it's an energetic particle, so yes, this is a. In principle, if you want to generate this, yeah, that's maybe an important thing. So if you don't like or you think that this is a slightly peculiar way, one way to think about the states, that this is the states generated by heavy probes. So if you consider more higher point amplitudes, so if you consider energetic particle, it generates this graviton, which is the same as a shockwave background. So in principle, we could have considered, instead of there were 4-point amplitude, 8-point amplitude, where each of the shocks is generated, but it's simpler to do the 4-point amplitude and consider the shockwave states. Now, we would like to arrange them in time, because I would like to address what is the meaning of commutativity. We observed that commutativity is some property of scattering amplitudes in GR. What is this property of this? To do that, we take the scattering amplitude. I should switch to another. We should take the scattering amplitude, multiply by a momentum preserving delta function. Then we want to take the wave functions for the shocks such that the delta functions arranged at some time. So it's I, U1, U1, E to Z. E to Z, I, E to D. So this object, let me call it Q over delta U. So depending on which U1 is larger, U1 larger than 2 or less than 2, it corresponds to the ordering of shock waves, first one and second, or the opposite. So now let me consider, and you can simplify this. You can simplify this integral using the delta functions, etc. The result is that this object is an integral I over du dt equals pi delta u t over using it. So you see that the delta u enters here, so and the integral in the t plane is as usual, so we have, say, cuts, and the integral in the t plane should be understood like this. integral that we get from minus some prescription. Minus infinity. Now let's consider this limit where the shocks coincide, and we want to arrange them 1 after 2 or 2 after 1. And see if the result, what does it mean? So if you take delta u to be positive, say, and take it to 0 from the plus direction, for example. Well, let me not take it to 0 yet. So, but if it's positive, you can deform the contour here as usual. It's negative, you deform it in the other direction. So we get the statement that for delta u positive, q of delta u is integral from 0 to infinity dt. E is a minus pi over 2 t over du delta u. Discontinuity in t. A. Here this is the t plane. On the other hand, if delta u is negative, we close it in the other direction. And we get, well, we get the same thing, but with the integral from minus infinity to infinity. So now we want to consider, as before, what happens if we take the limit of coincidence shocks and compare two ways of arranging them. So we take delta u to 0, and we take delta q, which is q plus 0, which is q minus 0. So if you do that, this is the non-commutativity of shocks. And if you do the things correctly, you see the statement that delta q is equal to 0 is the statement that this k is equal to 0. So this is a statement that shocks commute. Now this statement has a name, which is superconvergence sum rules. Studies in the 60s. It's you get this kind of statement trivially. Imagine you take an amplitude, and you take a contour around random point. It's analytic, so it's 0. So if you get arcs plus integral dt is ta equal to 0. So if you can draw arcs, then you get that the integral of the discontinuity is equal to 0. Of course, you cannot draw arcs in general. So you can only draw arcs as in the previous talk, when the amplitude here is it should decay larger than should decay faster than 1 over t, because then this integral of arcs is 0 as you deform the contour. I don't know, is it clear? Yeah. And people study this in QCD, because you can add some polynomials, and then the discontinuity is dominated by resonances. That's how they tested the experiment and describe experimental data. So the idea is that, therefore, that you see that from this point of view, we started with just a propagation of geodesic helmet shock with background, and we saw that this fact that things do not depend on the polarization of the graviton manifests themselves through commutativity of shocks. And now we restated this statement as this, and you see that this statement follows from some property of the radial limit. Excuse me, how much? Okay, great. So therefore, we concluded that from this part of the talk is that the commutativity of shocks is related to superconvergence. And the commutativity of shocks is related to this sort of GR equivalence principle, and superconvergence is related to radial limit. It just follows from the property of the radial limit. So therefore, if you want to study, now we can study the modified gravity. Take any theory you like, and let's try to consider superconvergence relations. And we should see if this type of equation holds or not. But maybe let me just give you an example before we go further. How does it work, and why is it related to this commutativity of shocks? So if you imagine you have a simple example, which is phi cube type of amplitude. So you have A, S, and T. So related, and I will write only exchanges in the T and U channel. So if you wish, this is so this is we have recall that we have two shocks. Say we have 3 and 1 and 2 and 4. And so the interaction was here. You see that if you wish, the radial limit. If you take the radial limit, which is, recall that so S plus T plus U is equal to 0. So if you take T equal to 0, T equal to infinity, the behavior is T minus alpha U over 2. And therefore, if you want to impose superconvergence, which tells you that, in a sense, here it tells you that interaction with the particle 1, which is say T channel, is the same as interaction with particle 2. In general, it should depend on polarization for gravitons, but if you want to say that it does not depend on this polarization, it's the same as alpha T equal to alpha U. And here it's clear that if you take T to infinity, the term which we want to be 0 for this to be true is exactly alpha T minus alpha U. That's an example. Now, a slightly non-obvious statement, but I hope to convince you that it's correct, is that, let me write now. And another feature of this example is that you see that here's a discontinuity in T is just a delta function. Imaginary part of 1 over T is delta function. So if we integrate over it, it gives alpha T, and this imaginary part of 1 over U, it's a delta function, also is a minus, and that's why alpha T minus alpha U is this. More generally, if you evaluate discontinuity as we discussed, but now what I'm saying is only true in a quickly coupled theories. The discontinuity of T, let's say we consider tree-level exchanges like here. The discontinuity of T is a pole. So as you compute it, you take the residues of the pole. And so for tree-level, which is another example, delta Q is nothing but sum over all states of all particles that you exchange. And here have one arranging of the particles, say to 3. And from this you subtract commutator where you exchange the shocks. 1, 2, x. Now, one famous fact about 3-point amplitudes and the 3-point correlators and CFTs is that they fix by symmetries. And you can write down the most general solution to any amplitude like that. And the claim, which you can check explicitly, is that every non-minimal coupling to gravity leads to Schoch's non-commutativity. That's, I guess it's not obvious. If you haven't looked ever at the GR amplitudes, you might not, I don't know if you can see it without computing it. But if you write down 3-point amplitude of GR and you will compute it in this kinematics, you will see that it's such that it holds. For example, the simplest amplitude, which might be of this type, is let's say consider non-minimal coupling to a scalar particle. So in this case, if you have 2 gravitons coupled to a scalar, the amplitude takes the form. So we take the polarization of this guy being E3 mu, E3 nu, E1 rho, E1 sigma. 3-point amplitude square, E1 square. Yeah, if you're not familiar with the statement, just believe me, that's a kinematical fact that all 3-point amplitudes are fixed basically because you cannot write Mandelstam invariants because particles are on shell. So you cannot write non-trivial functions, it's just numbers. And if you evaluate this thing in the kinematics of interest, which is a Schoch-Waves kinematic, you get something like TU squared, and here you get the polarization of a probe times the momentum of the shock squared. So this is a probe, and we see that now if we propagate through shock waves in some order 1, 2, we get delta Q, E3 Q1 square, Q4 Q2 square minus square 4 Q1 square. So that's non-zero. The claim is that that's true for any non-minimal coupling to GR, to gravity.
That includes also conformal coupling, scalar with a rigid scalar.
Yeah, I think, well, for example, for graviton, graviton phi, this is the only non-trivial structure one can write, at least on shell. I don't think in terms of just on shell structure. And so this is non-minimal. And for
Sorry, maybe a silly question. So what does exactly non-minimal mean? Are like higher derivative corrections to gravity?
Then if they modify 3-point couplings, so any, no, so non-minimal couplings are 3-point couplings. Let's say I compute, take just pure GR, compute 3-point amplitude, or take a matter and minimal and couple it to GR, to gravity. And I compute 3-point coupling in this theory. This is a minimal coupling, and this is a particular set of structures. For example, for 3 gravitons, you can write 3 structures. Only one of them appear in GR, so other 2 I call non-minimal. And if you turn them on, you will get non-commutativity of shocks.
But what about, let's say that you replace like R to the, like the kind of things you get in a string theory, right?
Oh yeah, so this is, so here I'm talking about this 3-point coupling. So if you say take say type 2B, you don't modify 3-point coupling, 4-point coupling, I have nothing to say. But
That's good.
yeah.
So this will be true in string field theory, or my local field theory it would be 0?
Well, actually, no. Well, yeah, so let's switch now to a more realistic example, which is string theory.
Yeah.
So let's discuss string theory, yes. But before discussing string theory, there is a big missing ingredient, which you might ask. So the real question is now, if we have gravitational theory, do we have to impose this condition or not? I mean, is it forced upon us or not? And here the situation is, or our understanding at least, slightly different in flat space and ADS. So in ADS, because we are talking about the radial limit, as I told you, this follows from the boundedness on the radial limit. And so in ADS for CFTs, we have a very good control of radial limit, so you can just prove that this is true. So in flat space, there are no rigorous bounds on the radial limit of gravitational theories. But one, at least, I thought a reasonable constraint comes from asymptotic causality. And at least in the, so you want to Shapiro delay to be positive. So there was a paper by Kamani et al. About that, and this asymptotic causality, it implies roughly that for physical t, s of t cannot grow faster than s squared, because otherwise you will start. So you can think of this as a propagation through a medium with some dielectric constant, and this medium becomes accelerating, at least in weakly coupled picture. But if you if you believe that this holds in general, and in ADS we definitely know that this just follows from the properties of CFTs, then you get that in any consistent theory of gravity, if you take this 4-point amplitude, well, you can take a high point amplitudes also, if you know the higher radial limits should be 0. So this is a new consistency conditions which we would like to impose on any theory. Now let's go to string theory and see how it is satisfied there. Because in string theory, in general, the coupling to graviton is non-minimal. So let's write the 4-point amplitude of gravitons in string theory. 4-point amplitude of gravitons in string theory takes the following form. It's a famous gamma functions factor. And here, this is completely universal, does not depend on anything. And here you have polarization factors, which are something like E1, E2, E4. K left. And the same, it's a closed equal open square like relation, so you have a left polarization factor and a right. So these polarization factors are of two types. So let me call one as so these are known factors. You can compute them in tree-level string theory. And they have there are two of them. One is a bosonic, and the second one is superstring. These are known functions. Now if you take superstring, you have k left and k right equal to this factor. If you take a heterotic string, you have one of them superstring, another bosonic, and in a bosonic string, they're both bosonic left and right. So then you can look, for example, at the coupling of three gravitons. And the coupling of three gravitons is coincides with GR here, but it's different, say, in a bosonic heterotic string. So the coupling is non-minimal. Therefore, if you look at low energies, there is some high derivative corrections which introduce this non-minimal coupling, and propagation is not allowed to geodesics. But clearly, this is a causal theory, and consistent with this picture, you get that in this theory, indeed, the Regge limit is such that this bound is satisfied, and therefore discontinuity vanishes. How does it come about? So if you compute, so recall we have this picture with a probe E3 going to. So we have probe 3 going to probe 4 and shocks. If you compute these factors for these kinematics, then, well, you get something which looks like E3 times E4 for this factor, and you get something which, for this K bosonic, something which is symmetric in 1 and 2. So it does not have a commutator. Plus, there is a very nice, this beautiful factor, which is introduced non-commutativity. So the important thing about this factor is that if you compute the discontinuity T at the graviton pole, it has this factor of T here, so it does not contribute to one pole, T equals 0, but it will contribute to the pole U equals 0. And similarly, there is a guy here with U in the numerator, so if you look just at the graviton, this thing is non-zero, so how come it's all 0? Well, not surprisingly, string states come and fix the commutator. So there are extra states. So if you compute the discontinuity of the whole thing, then you get the formula of the type where you get this non-commutative factor coming from here, something of the type that we consider for the non-minimal coupling of scalar. And here you have one coming from a graviton, and then in this discontinuities there are all string states. And this is the residues of the string states and their couplings, and you can check that this sum is indeed identical to 0.
So these are massless strings?
Oh no, they are massive string states. Massive string states, yeah. And the picture here is that yeah.
They are all the intermediate states of the
They are all the states that you exchange here between the shocks. So, and this is, well, this whole thing was also motivated by this discussion about Shapiro delay in the modified theories of gravity, where we saw that if you modify proton couplings, then you violate causality. And then the higher speeds or the extra state should come in and save the day. It's the same picture here, that if you modify the coupling to a graviton, there are extra states that come and save the day. But the difference between this is now an equation. So it's
So I don't fully understand the
Yeah.
role of alpha prime in all this.
well, it's so if you have a modification of GR, for example, it comes with some scale.
Yeah.
Let's say call it gamma.
Yeah, that I understand.
And then there are also states which are alpha prime, so which
Yeah.
contributes to this dependence of alpha prime. And then the whole thing, so note that this function is a function of
Yeah.
S and T, so this should be satisfied for everything.
Yeah, for all alpha prime.
Yeah. So there is this identity, and in string theory it is satisfied, and therefore this is one way to solve it, to satisfy this constraint. Another way is, for example, if you have electrons and you integrate out electron at one loop, and you look at the gravitational triangle, it modifies the coupling, but again, in electromagnetism, there are extra states, which are two electron-positron states, which are exchanged, which restore the commutativity. Yeah. So that's a punchline. The punchline so far is there is this equation, which is a consistency conditions on the gravitational theories, and if you start naively modifying GR, you will generically violate that. So you have to make sure that it's not violated. And another interesting connection is that.
Sorry. So should this be true also if you go to higher genus? Let's say you go to genus
Yes,
1
this
and
is,
string theory.
so this is a little bit funny because so here so something like this should be true in a full theory, and
yeah, but perturbatively. it's not.
conservatively you will violate it, and so the same as happens at genus 1. So you cannot. It's an interesting question. We haven't fully understood it, but you cannot naively expand in 1 over n, because if you expand with 1 over n, your amplitude starts growing very quickly, and you have to resum, which is this canalization, blah blah blah. So yeah, another little comment is that if you to connect to the previous discussion is that this type of object appears if you start evaluating. So we had this partial waves, and we said that they're analytic in spin, and if you consider scattering of gravitons, the only physical partial waves which appear here are even spin because it's identical particles, but the non-commutativity of shocks are related to properties of the partial waves at spin equal to 3. So it's it. So that's one example where you could have said, okay, there is some analyticity in spin, you can analytically continue, but what is the meaning? So well, here, for example, you see that at this non-physical spin, you start probing this shockwave states. Now let me finish and just restating it in the context of ADS-CFT, what I just said. And so let me move to the table. How much time do I have?
6 minutes.
Okay, so let me do now flat space and ADS. So here we have shockwave states, and they were these funny states which are not quite physical in the usual sense. And so in ADS-CFT, shockwave states correspond to light ray operators. What is a light ray operator? You take an operator and integrate it along some line. This is, for example, famous ANEC operator. And here, the fact that these are not physical states, or these are perfectly well-defined physical objects, but they annihilate the vacuum. So if you act with the state on the vacuum, it is 0. And if you look, if you use the usual idea CFT dictionary, you see that these things generate shockwave states in the bulk. So this asymptotic causality, or Regge bound, here is just a rigorous bound on Regge, which is very well under control in the CFT. And so here it's completely rigorous. If you were following some of the recent Bootstrap developments, one of the power of CFT is that you can bound on Regge, and therefore you have this thing, you can have a good control on the Regge element. So here we had a commutativity of shocks. And in the CFT, this is a commutativity of ANEC operators. ANEX. They also, so this operator integrated along that line, and it's also inserted at some fixed transverse position. So ANEX at different transverse positions should commute. Sometimes this was, for example, there was a paper of Hoffman and Mandelstam in 2008. They consider these operators, and they sort of claim it as a trivial thing. And the argument was that if you take two operators which you put on the same null line, they separated transverse space, and therefore they commute because they're space-like separated. That was the argument. This is space-like separated operators, they have to commute. But this is slightly too quick, because if you draw these operators on a cylinder, they're indeed separated everywhere, but they touch at infinity. So if you draw a null line on a global cylinder, you will see that there is a coincident point here, and you have to worry about commutativity of these guys, and in general. So you can come up with examples where these light ray operators do not commute, even though you could have run this argument, look, they're space-like separated, so it's beyond that. So there was a superconvergence, and this becomes a statement about T and U channel OPE. So this exchange of particles was nothing but the T channel OPE, and discontinuity is a sum over blocks, and you can compute the corresponding blocks. So there is a slightly different kinematic, so the blocks which appear here are slightly different. So there is a similar connection and it was known actually in QCD for a long time. This operator is also an energy calorimeter operator, so if you want to discuss event shapes, so if you have some collision, you measure energy fluxes. This is the operators which control them, and indeed, for example, the OPE of these operators is related to OPE at position on physical spin 3. And again, so there is this Froissart-Weber formula here, which becomes this Coron-Miller formula, which probably Fernando will explain. Right, and apart from this gravitational discussion, there is a mass applications of the story of to collider physics, because we learned how to. So recently there was a progress on understanding these light ray operators. For example, we understood how to do the OP of these guys. It might be useful for even maybe some QCD computations. I'm not sure. But that's the basic story. So if you try to modify EGR, bound on Regge tells you that you should be very careful, in particular if you naively introduce some non-minimal couplings. You have to have this infinite number of particles which come in. And so this non-commutativity of shocks are related to A minus C. So if you wish that the fact in a CFT, if you're familiar with 3-point coupling, so this equation that we got is of this type A minus C plus something has to be equal to 0. But yeah, it's to be seen exactly how much we can learn from this. Thank you.
Questions?
In your identity, the sum over intermediate state, those were off shell, no? X equal to
yeah.
X.
So no, they were on shell because we take this continuity of amplitude, so we put them on shell.
Still I will try. That the identity being zero in string theory, doesn't that follow from just gluing? You know, it's geometrically kind of maybe glue geometrically. That's a 3 vertex, no? A is essentially a 3 vertex.
Right.
And then.
Well, now the thing is that if you have and the non-trivial fact is that if you glue it like this,
Yeah, it's different.
it's different than glue it like that.
I
Because,
agree.
but the consistency of the theory in
Then
particular.
it's not true.
No, it's true in string theory. It's true due to string states.
I know, you showed.
Yeah.
I don't see it from blue.
Right. I mean, it's not true. It's not true because you get this commutator, but then the rest arranges itself to cancel it.
Yeah, sorry, let me ask you the question again, and it's related to that and to the string states. If you take the Virasoro-Shapiro amplitude and you take alpha prime to 0 limit, you get just the usual string theory, GR amplitude.
Yeah.
And that one, does it
So
satisfy
alpha prime, it will violate. It will violate that. You will get Gauss-Bonnet, for example. So you will not get this contribution.
But then you say that this is equal to 0 regardless on alpha prime.
That's true. Yeah. So.
But if you take the limit alpha prime to 0 and then you do the computation, it's not.
Yes.
Gauss-Bonnet goes to 0, right? In the same limit.
Yeah,
That's
it's
multiplied by
the
alpha
same.
prime.
It's the same coupling. So if you take alpha prime, yeah, sorry, very good. Yes, if you take alpha prime to 0, Gauss-Bonnet goes to 0.
So this also
So
works
alpha prime here is
for
here.
the limit alpha prime going to 0.
Yeah. So the way it works is you have alpha prime here and alpha
Yeah.
prime sent to 0.
Yeah.
So thank you. Sorry. My bad.
Other questions? Well, thanks, Chancellor.